Okay, so another operation that's important for matrices is called matrix multiplication. And this is not as straightforward as matrix addition. Matrix addition is good and useful. Matrix multiplication is one of the most important arithmetic operations of the of all time. Okay, so but it is much more complicated than matrix addition, so it's worth talking in detail about this. So I'm going to do this via build up some examples to build up some of our understanding of this relatively complicated operation. Okay, this is nothing that's beyond your ken or anything like that, but just when you compare it to matrix addition and other types of arithmetic operations that you've learned in your life, yeah, it is much more complicated. So let's take a look. Matrix multiplication. So let's take, for example, a row vector and a column vector. All right. And let's take a row vector. So let's just do an example. I'm going to define for you what I mean by the product of, let's say, a row vector like 1, 2, 3, and a column vector like 4, 5, 6. Okay. So just to be clear, this here is a 1 by 3 matrix. And this here is a 3 by 1 matrix. And remember, we call 1 by m matrices, we call those row vectors. And we call things of the form which have dimensions n by 1, we call those column vectors. Okay? Now, how do I define the product of these two matrices? Here's what I'm going to do. I'm going to do 1 times 4. I'm going to write it down and I'll explain. Plus 2 times 5 plus 3 times 6. This is how it's going to be defined. I'll explain, but let me just compute this. This ends up being 4 plus 10 plus 18, which I believe if I have 28, 32. That's the product. In other words, the product ends up being I'm going to think of it as a 1 by 1 matrix. So I'm going to think of all of these as being a matrix with just one row and one column. It's going to be 1 by 1 here. Now let me go back and explain how I did this. I have this row vector here, and I have this column vector here. And what I'm going to sort of do is interleave the first entries of these things together by multiplying them together. And when I write this multiplication right here, this is just ordinary multiplication like you learned in elementary school. Okay? And then I'm going to add to that the product of the second entries, 2 and 5. Okay? And then finally I'm going to add to that the product of the third entries, 3 and 6. And that's how I obtain this product here. Now, notice that it was crucial that the number of entries in this vector here was the same as the number of entries in this column vector here. Because that's what allows us to sort of pair off these entries, the first entries with the second entries and the third entries, to pair those off and then assemble this sum in this way. Okay? This is how we define matrix multiplication in this particular situation. Let me show you another example, slightly more complicated. Now I'm going to take a 2 by 3 matrix. Let's take the matrix 1, 2, 3, 4, 5, 6 and multiply it by the 3 by 1 matrix 7, 8, 9. Okay, so to be clear, this matrix here is now 2 by 3. And this column vector here, this is a 3 by 1 matrix. Okay, what happens when we multiply these things together? So I claim, and I'm right, that what we're going to end up with is a 2 by 1 matrix. It's going to be a 2 by 1 matrix, so it's going to be an example of a column vector. It's going to have 2 entries. And these two entries are going to be obtained by interleaving the first row with this column. That's going to be the first entry. And then interleaving the second row with this column. By the way, let me just throw some terminology for those of you that know it. This kind of operation where we're interleaving in this way should feel very familiar. You might know this as a dot product, right? If you've ever learned about the dot product before, this feels like a dot product of two vectors. And indeed, that's a great way of thinking about it. Now, to obtain the first entry of this 2x1 matrix, it will eventually be a 2x1. To obtain this first entry, what I'm going to do is take the dot product of this first row here with this column. So I'm going to get 1 times 7 plus 2 times 8 plus 3 times 9. That's my first entry. My second entry is going to be what I get by taking the dot product of the second row with this column. And what I get here is 4 times 7 plus 5 times 8 plus 6 times 9. And oh my God, I'm going to have to do this arithmetic now. And if I do this arithmetic, this is 7 plus 16, which is 23, plus 27, which I think is 50. And then this is 28 plus 40 plus 54. Which is 68, 118, 122. I'm guessing. I don't know. You check me. I guess it matters if I get it right. Should I just do it again? 28, 40, 54. So that's 94, 102, 122. Okay, it feels right. Yeah, 122 feels right. Okay. Anyway, that's the product. The product of this 2x3 with this 3x1 ends up being this 2x1 matrix here. Okay? Okay. What happens if we expand out this 3x1 to a 3x2? What happens then? So let me do this in purple. So let's say that we have this same first matrix here. 1, 2, 3, 4, 5, 6. Then we go to 7, 8, 9, and then oh gosh, let's make it easier on ourselves. 0, 1, 2 here. Okay. So what are the dimensions that we're talking about here? This is 2x3, and this one is 3x2. Can you guess what the dimensions of the product will be? It'll end up being 2x2. Now I'm trying to sort of jog your ability to like put together patterns here, because everything that I'm writing here is true. So maybe you're able to notice some patterns emerging. Let's see if those patterns keep holding. So let's see. I'm going to end up writing down a 2x2 matrix, like I said. What I'm going to do to get the entries of this 2x2 matrix is I'm going to, again, take dot products. But now I'm going to take the dot product of the first row with the first column to obtain my first entry, the 1, 1 entry of my product matrix. When I say the 1, 1 entry, what I mean is the entry in the first row and the first column. That's this entry right here, the upper right entry. This is a 2x2 matrix, remember, or gonna be a 2x2 matrix. Okay, so what happens when I take the dot product of 1, 2, 3 with 7, 8, 9? Well, I did that right here, and I found that the answer was 50. So I hardly have to think. This one is 50. Okay? And similarly, to get the 2, 1 entry, I take the dot product of the second row with the first column. And I've already done that calculation right here. So what I get is 122. Okay? To get the 1, 2 entry, that is the entry, this might be denoted A12. To get A12, the entry in the first row, second column, what I do is I take the dot product of the first row of this matrix with the second column of this matrix. So what I end up getting is 1 times 0, which is 0, 2 times 1, which is 2, plus 3 times 2, which is 6. So I believe that ends up being 8. Okay, and finally, 4, 5, 6, we interleave that. We take the dot product of that, rather, with 0, 1, 2 to obtain this entry right here, the 2, 2 entry of the product. And what I get is 4 times 0, which is 0, plus 5 times 1, which is 5, plus 6 times 2, which is 12. 5 plus 12 is 17. Okay? All right. So, to summarize all of this, okay, and you should scrutinize these examples because you're going to be doing this operation quite a lot in your life. But to summarize all of this, okay, I'm going to write the following sort of fact. So, matrix multiplication. Well, let me say it like this. If A and B are matrices, then we can form the product, which is the result of matrix multiplication, AB. We denote this just like this, A times B. If the number of columns of A is equal to the number of rows of B. Okay? This is the only time we can do it. Okay? So if A and B have if this is not the case, if the number of columns is different from the number of rows of B, then we cannot form the product of A and B. It doesn't make sense. It's undefined. Let me give you an example of what I mean by this. So, like, let's say that we were to try to form the product of 1, 2, 3 with the matrix 2, 1, 1, 6, 7, 8. The problem here is that this matrix here is 1 by 3. No, I'm sorry, I got that wrong. It's 3 by 1, rather. It's a column vector, 3 by 1, 3 rows, 1 column. Whereas this matrix has dimensions 2 by 3. The number of rows of this matrix, if we call this matrix here temporarily A, the number of rows of A is 3, and that's different from the number, sorry, my bad. The number of columns of A is 1, and that's different than the number of rows of B. In other words, this number and that number are different. And when this number and that number are different, you cannot form A times B. AB here does not make sense. We cannot compute A times B. Cannot be computed. Because again, the number of, I mean, just try. Like, imagine you were to try. You would take this row here and interleave it with this column here. But you see there's just not enough numbers in this row, right? The only way there could be enough numbers in this row is if we add another column. In which case this 1 would bump up to a 2, and then the number of columns would agree with the number of rows of B, right? Unfortunately, we don't have that. But my claim, and I'm right, is that any time the number of columns of A is equal to the number of rows of B, then we're good, okay? All right. So in particular, if you have two square matrices, then the only time that you can multiply them is if their dimensions are the same. So you can multiply a 3 by 3 with another 3 by 3, or an 8 by 8 with another 8 by 8, but you can't multiply a 3 by 3 with an 8 by 8. Again, there's a dimension mismatch, as we call it. One other note. If A is m by n, okay, and B is n by p. And understand, these are referring to the dimensions, the number of rows and columns. Then a times b is m by p. Okay? So it's like when you have an m by n being multiplied by a n by p, this is just shorthand, this is not formal notation or anything. It's like the n's get glommed together, okay? And then you're left with an m by p. That's the idea, okay? Okay. I don't want to say too much more than that. Okay. Let's take another example. Let's look at the product of two 2x2s. So let's call A here. We'll take the matrix 1, 2, 0, 3. Oh, and let me not make you think that all of these entries have to be positive numbers. They don't. So like -1, 3, 2, and -2. I just don't want to use gross fractions or anything like that because we're going to have plenty of that in the not so distant. All right. Then pause the video for me and compute A times B. Go. Pause the video and compute A times B for me. Okay, did you do it? I think you get, let's see, -1 plus 2, which is 3. I'm not very good at arithmetic. Just bear with me. So 3 times -2, which is -1. What? I don't know what I just said out loud. 0, 6. 0, -6. This is what I got for A times B. Does that look plausible? I honestly can't tell. Should I review? -1 plus 4. Feels right. 3. Yeah, that looks right. Oh my god, I think I did it right. Okay, good. Okay, now I want you to pause the video again. And I want you to compute B times A. Oh. B times A now. In other words, do it in the other direction. In the other order, rather. Maybe that's a better way of saying it. Do it in the other order. Okay, pause and then... yeah. Okay, did you do it? That means I have to do it. Okay, so -1. So now I'm going to take the first row of B and interleave it, take a dot product with the first column of A. It's very easy to confuse yourself here. -1, -1, 3. So I think I get -1. Then I take the first row of B and dot product it with the second column of A. Get -2 plus 9, which I believe is 7. Then I take the second row of B and dot product it with the first column of A, and I think I get 2. And then I take the second row of B and interleave it or dot product it with the second column of A, and I get 4 plus -6. I think it's -2. And do you see something crucial here? Crucially, matrix multiplication is not commutative. This is so important. Okay? It's important for everything. The non-commutativity of, and what do I mean by commutative? Like real number multiplication is commutative. If you have two real numbers, x and y, you know that it doesn't matter what order you multiply them in. X times y is equal to y times x. Not so with matrices. A times b is not necessarily the same thing as b times a. Okay? Okay. So some properties maybe of matrix multiplication that I should mention. There will be plenty of time for practice and things like that. Properties of matrix multiplication. So one is that how matrix multiplication interacts with sums. So let's say that we have A and B being the same sizes. So let's just assume whenever I write something like this, that the dimensions of the matrices A, B, and C they all work out so as to make these operations make sense. Okay. Then in this case, where you're taking A plus B and multiplying that by C, this is equal to AC plus BC. And I want you to pay close attention to the order in which I write these things. Because if I wrote CA plus CB, that would be incorrect. Because remember, matrix multiplication is commutative. And I'm multiplying C from the right. I'm multiplying A plus B on the right by C. And so the distributive property kind of looks like this, where the C lands in front or to the right of A and B. And that's what I see here. So let's contrast that with this property, which is also true. If you do C times A plus B, well, this ends up being CA plus CB. Again, the order in which I write these things really, really, really matters. Okay? All right. What else? Matrix multiplication, it might not be commutative, but it is something called associative, meaning that you can write if you have something like A times B times C, okay? This is the same thing as doing A times B times C, like this, where you do BC first, then multiply by A on the left. That's the same thing as doing AB first and then multiplying by C on the right, okay? What wouldn't be okay is if I was to somehow have a product like ACB. That would not be the same thing as ABC because of commutativity, okay? And so very often we'll just drop parentheses altogether and just write this. This is called associativity, and it's important. Okay, let's see. Is there anything else I want to say about, I'm just looking quickly at this reference here. Is there anything else I want to say? Maybe one more thing, which is that let's say that you have some real number, k. Okay, if you have some real number k, if you multiply a matrix by it, or a product of two matrices like this, then one way of thinking about this is that you're going to take Ka and then multiply that by B. That's legit. But not only that, you could also multiply the B by the K first and then multiply that by A. This is also the case. Okay, so constants like K, so K here is just a real number, or a constant, I'll say. It can like float around inside of a product of matrices without issue. All right. Okay, that's enough for matrix multiplication. In the next one, I want to talk about something called the identity matrix, and then talk about something called the inverse of a matrix. Okay, so this sort of relates to the concept of matrix division. Okay, let's do that in the next one.